Hey there. Let's chat about probability. Some of this stuff is kind of some basic things, and I'll just kind of breeze over it pretty quickly. Some things might be new to you. Maybe all of it's new. Who knows? All right. On probability, in general, when you are looking for probability, there's a basic way of finding that, and that would be, and this is maybe some new notation, the probability of some event occurring, that's what this is, the probability of some event occurring is going to always be equal to the number of successful outcomes there are out of the total possible outcomes there are. Probability of some event will always fall somewhere between a 0 and a 1. 0 meaning it cannot happen at all, 1 means it's guaranteed to happen. We usually will write probability as a decimal or a fraction. It can be a percent, but typically we leave it as a decimal or a fraction. The multiplication principle is one of those basic rules that maybe you've heard of, or maybe it's new. It can be pretty simple. It can also get more complex. It's the principle that states that the probability of A and B occurring, if I want something and something else to happen, then you're going to multiply those two probabilities together. The one thing that you have to watch out for when it gets tricky is whether those two things happening are independent or if they're dependent. Let's look at a few examples. Let's look at rolling a dice twice and getting an odd number and then another odd number. So you start off with the first one, the probability that I get an odd. Well, there are 3 successful outcomes, 1, 3, and 5, out of 6 total possible outcomes. And, so I'm going to multiply, another odd number. Now these are what we would consider independent events because what I rolled on the first one has absolutely nothing to do with when I roll it the second time. These are independent of one another. That would end up being another 3, 6. Ultimately, I would probably reduce these to 1/2, and a 1/2 times a 1/2 would be a 1/4 probability. On this next example, we're picking 2 cards from a deck, and we're getting 2 aces. Now this will be without replacement, so once we grab that card, we're not putting it back in the deck, we're just grabbing another card from the deck. That's an example of dependent events. Let me show you how. I'm going to pick this first card, and I want it to be an ace. That would be 4 successes, because there's 4 aces in the deck, out of a total of 52 cards in a deck. And, so I'm going to multiply. I'm going to do this again. Here's where I have to adjust my probability because this whole without replacement means I didn't put the card back in there. So there's only 3 aces now, there's only 3 successes, and there's only 51 cards in the deck. And again, I'm going to multiply these. I would reduce first, this would reduce to 1/13. This reduces to 1/17. And then when I multiply those, I get a 1 out of 221 probability. And you might want to approximate that. And I have pretty low probability, 0.00. And here's the thing with going decimal is a lot of times it's a rare thing, and so you got to put a lot of decimal places before it ever really gets you anything. I'll go 0.0045 on that. All right, last example. Picking 2 cards and getting 2 aces with replacement. All right, this time I'm going to have 4 successes out of 52 cards in the deck, and then I'm going to do it again. But this time I replaced that first ace, so I still have 4 aces in the deck and I still have 52 cards. And then I'd go ahead and reduce these to 1/13, 1/13, and 1 over, I think that's 169, and then as a decimal, I get 0.0059, slightly more likely because I put that card back in there. I put this slide in here to show you because a lot of the the examples we do, we're rolling 2 dice. You're rolling 2 dice and seeing what you get out of that. And this is just a breakdown of what all the possible outcomes are when you roll 2 dice. You could roll a 1 and a 1 right here, or a 1 and a 2, or a 1 and a 3, and a 1 and a 4. And notice that a 1 and a 2 is actually considered different than a 2 and a 1. It's almost like these are colored dice, and the red dice is different than the green dice, or something like that. Now, what I like about this is that it shows you if you have all these possibilities, there are 6 times 6, 36 different possibilities. So when you're looking for your total, it's always over 36. The other thing that's nice about this arrangement is you can see that these diagonals are always the same sum. These are all the ways to end up with a 7. You can see them boxed in. And then these would be all the ways that you end up with a 6. And that likelihood would be the same as the likelihood of getting an 8, which is this diagonal over here. Down here, very rare to get a 12 or an 11 kind of thing. You probably will use that for your homework. This is what we call a probability distribution, which shows all the different ways. It kind of shows this same thing, but it graphs it out for you. So you can see, oh yeah, 7 is the most likely event because I have the most ways I can do that. The next principle is the addition principle. And you use this one when you're looking for the probability of A or B occurring. If you see an or, and always means multiply, or always means add. Now, the tricky thing about this is you have to consider whether these two events, this A and B, are these mutually exclusive. Are they totally different things, or could they have happened at the same time? I'll show you what I mean here in a minute. This first one, rolling a dice and getting a 4 or an odd number. Well, these are considered mutually exclusive because you could not get a 4 and an odd number at the same time. Those are totally different things. So you just go through it. Probability of getting a 4, well, there's only one success out of 6 rolls, 6 possibilities. Or an odd number. Well, there's 3 odd numbers in the dice, so that's 3 out of 6. And I'm going to go ahead and leave it in 6 because it adds together nicely that way. That's 4 6, which would end up getting you 2/3. Next example. Picking a card and getting a king or a queen. Again, these are mutually exclusive. Those are different things. There are 4 kings, so I'd have a 4 out of 52. Or means add. 4 successful cards that are queens out of 52. That would reduce to, or that, I'm sorry, when you add that, that would equal 8 over 52, which can reduce to 2/13. This last example is the one I was talking about where these are not mutually exclusive. It says picking a card and getting a king or a heart. Well, I'd start off and say, well, a king, let's see, there's 4 out of 52 of those, or getting a heart, well, all the hearts, there's 13 of each suit, so that'd be a 13 out of 52. And then I could add those together. The problem with this, though, is that in this probability right here, I counted the king of hearts, but I counted the king of hearts right here also. So when I'm doing that probability, the king of hearts got counted in 2 places. If they are not mutually exclusive, like in this case, you have to subtract that whatever gets overcounted. So I had 1 card that got overcounted, so I'm going to have to subtract a 1 out of 52. Ends up actually being 16 out of 52 then. And if I reduce that, that would be a 4/13. All right, so then these were some examples that we did in class. I actually kind of think, well, I'll have you go ahead and pause and see if you can work through these, and then you can come back and I'll have all the answers posted for you. But don't just wait me out. Just go ahead and try. You can do it. Pause. All right, real quick, let's go over those. And that first one, The sum is either 9 or 3. I just went back to the chart. There were 4 ways to get a 9. There were 2 ways to get a 3. There's my 6 out of 36 possibilities, and go ahead and reduce that. The second example, again, went back to the chart. Less than 5 means it'd be a 4, a 3, or a 2. There were 6 possibilities of all of those. And then on this last one, because I'm not replacing them, the number of possible diamonds reduces, as does the total number of cards in the deck. So those numbers reduce. I went ahead and just canceled a lot of stuff, but in the end, it was such an ugly fraction. I went ahead and went decimal, and I kind of ran out of room. I think it was actually a 495, and so probably should have rounded that up, but I ran out of space. Let's move on. A probability distribution is when you're looking at all the different ways something can happen, and there's like this list of all the different outcomes. So in this case, if you think of a bag of M&Ms, Google says this is supposed to be the breakdown of how many colors of each type there are. So let's look at a few probabilities. Given that information, you're going to grab one M&M. What's the probability that you get an orange or a red? These are mutually exclusive. I can't pull an M&M out, one M&M, and have it be orange and red. So I'm just going to go with probability of orange is 0.2. Or tells me to add, probability of red is 0.13. All right. In an effort to kind of hurry up the video, a lot of this you're just going to type that in your calculator, get an answer. I'm going to get a little bit lazy on us, and I'm just going to show you how to do it. I'm going to do an equal sign. I'll let you do the math on it, figure out what that would add up to. Grab 2 M&Ms, find the probability you get a red, and then a blue. All right, so the first time I have to get a red, all right, that's a 0.13. And then a blue, and tells me to multiply, and blue is 0.24. Multiply those together, you'll have your probability. Now this is where it gets a little bit trickier. It says grab 2 M&Ms and find the probability that you get a green and a blue. Because you're getting 2 of them, right? You're going to get a green and a blue one in either order. So that's a little bit sneaky, because you have to look at the possibility that it went green and then a blue, or the possibility that it went blue and then a green. These are considered different things, so we have to look at that. Now if you go through it, probability of green is 0.16, and it tells me to multiply. Probability of blue is 0.24. Or, so I'm going to add that. Blue is 0.24, and means multiply. Green, 0.16. So then I'm going to have to type that in, and really it's the same thing regardless of the order that you do that. When you multiply those together and then add them up, or just take it times 2, however you want to do that, I end up with a probability of 0.0768. Let's look at that without numbers quite so nice in a chart for us. It says if it rains tomorrow, the probability is 0.8 that John will finish his school project. All right, it's rainy, he's going to stay inside. If it does not rain tomorrow, there's only a 0.4 chance that he will finish it. So he's going to go outside and go enjoy the beautiful weather, I guess. Suppose the chance for rain tomorrow is 60%. What's the probability that John will get his project done? All right, I'm going to go ahead and look at this like it's a tree diagram. It's kind of basic to do tree diagrams, but it's a nice visual, and it is, if you do the question help on Math Excel, it's how they're going to do it. So you're going to start off with looking at whether it rains or doesn't rain. So I'm going to abbreviate here. I'm going to say it's either going to rain or we're going to go no rain. Now if it rains, well, first of all, I guess what is the probability it rains? So I'm going to go, instead of 60%, I'm going to put 0.60. And if there's a 0.60 chance it rains, that means there's a 0.40 chance that it does not rain. All right. Now, if it does rain, I have 2 things that might happen. He might finish his project, he might not finish. Let's go F for finish, NF for not finish. And so that might happen over here also. He might finish or he might not finish. Looking over here on the left side. If it rains, because this is the side that it rains, 60% chance that it rains. They said that if it does rain, the probability that it finishes is 0.8. So that would be a 0.8. And that means that the probability that he doesn't finish would have to be a 0.2. Just subtracting from 1 to get the opposite. Over here on the 0.4, on the not raining, if it does not rain, there's only a 0.4 chance he's going to finish. So I'm going to put 0.4 right here, which means there's a 0.6 chance that he does not finish it. Now you have to look at, the question was, what's the probability that he will get his project done? Well, getting his project done is either going to happen at this spot or at this spot. But it's more than just the 0.8 and the 0.4. It's the 0.8 after the 0.6 of it raining, or the 0.4 after the 0.4 of it not raining. So what you end up doing is over here on this side, well, this is the probability that it rains and that he finishes it. That's what this is right here. I wouldn't probably do the big tree diagram. I would just kind of say this in my head or write it or whatever. Probability that it rains is 0.6, and, so that means I'm going to multiply, he finishes 0.8. I would multiply those things together. Or the other option, so that's a plus, the probability that it doesn't rain, that's 0.4, and, so I'm going to multiply, he finishes his project. So you can do the tree diagram if you want. I typically just write this out and go ahead and type that in. I told you I wasn't going to do all this, but I can't help myself. I just finish him. Okay, there's my probability that he actually finishes his project tonight. I'm going to start something new here. We kind of wrapped up there, talked about different ways of doing probability. One of the things we have to watch out for is when you're doing probability, your denominator is always the total number of ways you can do something. Sometimes that's simple, like, well, there's 6 ways I can roll the dice, or 52 different cards I could pick. That's sometimes easy. Other times that gets way more complicated to figure out how many ways something can happen. We have counting principles then that help us figure out what's the total number of ways I could do something. We have 3 different types of counting principles. The first one, probably my favorite, is fundamental counting principle. I like it because it's kind of visual. You can see what you're doing. But ultimately, you're just going to use the fundamental counting principle if you need to be able to repeat values. That's the biggie. The fundamental counting principle allows you to do some repeating of values, get the same thing more than once. The other thing to remember is that order is important on the fundamental counting principle. One of the other things that's nice about the fundamental counting principle is you can tweak it to do what you need it to do. For instance, here we go. How many possible license plates are there? Well, if you think about it, my license plate goes letter, 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 number, number, number. And I use dashes to kind of show that. Letter, 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 number, number, number. And I'm always multiplying between that. When I put my numbers in, I'm always multiplying. I get lazy about putting that dot there, but that's what I'm doing. So how many possible letters could this first one be? Well, it could be 26 different letters. And then my second letter, because you can do repeating, you can use an A and then an A again. That's what fundamental counting principle is nice about, because you can then say, well, then 26 for that one and 26 for the third one. Then I have number, number, number. Well, there's 10 possible numbers, 0 through 9, and I can repeat them, so it's going to say 10 for all 3 of those numbers. Now this is my license plate. My license plate goes letter, 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 number, number, number. However, I don't know if you realize this or not, some license plates go the other way. They go number, 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 letter, letter, letter. So this would actually be an OR. So I'm going to put a plus. I'd have all of those options. Plus I'd have 1, 2, 3, 1, 2, 3. The other way around. 10 times 10 times 10 times 26 times 26 times 26. Now that's going to be the same number regardless of what order I'm doing it. And so real quick, that would end up being, this number over here is 17 5, 7, 6, 1, 2, 3. And so this number is the same over here. Add them together or double it, whatever you want to do. So we have 35 million different license plates that we could come up with in Kansas. If you ignore all the extra restrictions and the extra special kinds of license plates, that's just kind of a basic problem. All right. The next question, how many ways can the outcome of a horse race turn out if you have all 15 horses? So it's like you're going in there trying to pick the order of all 15 horses. Fundamental counting principle would look like this. I'd have 15 dashes out here, and I'd pick how many options do I have for first place? Well, I'd have 15 horses I could pick. Now, it says that I can repeat. But I can tweak it so that I don't repeat because I can't pick the same horse to get first and second. It's got to be a different horse. So there aren't 15 options, there are 14 options now. And then I'd have 13 and I'd have 12 and 11, ... It would keep on going down, all the way down to 1. Now that's going to be tedious to enter into my calculator. There is a notation for that. Do you remember that notation? That's really just going to be 15 factorial is what that's called, and it looks like an exclamation point. If you take a number times every number below it, that's just a factorial, and that's in your calculator. Let's go find that in our calculator. It'd be, I'd hit 15 first, and then I go to math, over to probability, and it's the fourth option there. And it will calculate that for you. And that's such a huge number there, I'm not even going to write it. It's 1.3 times 10 to the 12th. There would be a lot of ways for me to pick those 15 horses in order. That's not typically what you're expected to do. If you go in there and make a bet of some sort, they don't want you to pick all 15 in order. Not going to happen. But there is a particular bet, it's called the win, place, show bet, that you're picking first place, second place, and third place. All right, so let's tweak that fundamental counting principle. Now I don't have to pick all 15 of them. I just have to pick the top 3. Well, I'd still have 15 options here. And once I've got first place designated, now I have 14 options for second, 13 options for third. Now that's a much more doable kind of thing. If you multiply those all together, there are 2,730 ways then that I could pick the top 3. Still not real likely I'm going to pick the right one, but there it is. Here's another question. How many ways could you answer a 10-question multiple choice math test? Now we're just assuming that you are totally guessing, whatever, how many different ways could this be answered? It's multiple choice, you have A, B, C, D options. Now it's really tempting on this. Everybody wants to say that there's, oh, well that'd be 40 ways then. It is way more than 40. If you have 10 questions, how many options do you have for the first question? Well, I'd have 4. And now I've got another question. How many options? Still 4. And 4 and 4 all the way down. And the easier way to write that would be 4 to the 10th power. And then you would go ahead and give that to me, write it out. So if you're just randomly guessing there, or just if I'm grading them, there'd be this many different, oops, sorry, I put that last comment in place. A million different ways there of people answering that quiz. All right, I'm going to move on to something different now. We've done some things with probability. Now I'm going to talk about some counting principles. When you do probability, the denominator is always the total number of ways something can happen. And coming up with that total number of ways sometimes can get tricky. It's not as simple as just there's 6 ways to roll a dice. Sometimes it gets harder. So we use counting principles to figure out how many ways can something happen. All right, we got 3 different things. I'm going to start with permutations. Permutations. All right, done with fundamental counting principle. Let's move on to the second counting principle. It's using permutations. A permutation is defined as an arrangement of objects. And so you're looking for how many ways can you arrange something. And if I go with how many arrangements, then order is going to be important on that. I cannot repeat anymore. Fundamental counting principle, when I'm doing those dashes, that's the only one that lets me repeat. Otherwise, we're going to always assume that it starts to decrease by 1. But order is going to be important here still. How many ways? Okay, so I'm going back to those same questions. How many ways can the outcome of a horse race turn out? Well, when I'm doing permutations, I do a capital P. I don't know if you've seen, you should have seen permutations and combinations by now. So I'm just going to kind of breeze through this. And it's the number of permutations. I have 15 horses, and I'm trying to pick all 15 of them and place them in order. Okay? That's a thing on your calculator. It's a calculation it will do. So depending on your calculator, it depends what operating system you have. I have to hit 15 first. And then I go to math, over to probability, and permutations is the second option. And then I put in my second number. Some of you get like a little box and you can fill in numbers, whatever, however you can get that put in. But I have that same number, that 1.3 times 10 to the 12th. Same huge number. I get the same answer, different way to do it. Same deal with the second question. How about if I just want the top 3 horses? Still permutations because I'm concerned about order, but I'm not allowing any repeating, so that's why permutations is working. I have 15 horses, but this time I only need to choose 3 of them in order. So when I type that in my calculator, same deal, get the 15, math, probability, option 2. Oh, looky there, it's still 2,730. Get the same answer, different way to do it. I don't know which way is your preference, either way works. The next one, how many ways can you pick a president, vice president, secretary, and treasurer in a club of 30 members? Here, order is important. It's kind of a big deal to be the president, so that's different than being elected to be the treasurer. So the order of those is important because those different offices represent different things. That's what's going to allow me to do permutations. And then I'm going to say I have 30 members and I have to choose 4 different officers. And then I would type that in my calculator and get whatever I get there. Okay, I'll go ahead and do it. 30. All right, lots of different ways for me to select those members. All right, that's it on permutations. Let's do the last one. Combinations. This one's pretty common because suddenly now we can't repeat, still can't repeat like we couldn't in permutations, but in combinations, order now is no longer important. That's a biggie for this. Anytime you're worried about order being unimportant, you go combinations. Here's an example. How many ways can you pick a committee in a club of 30 members? That's different. If I'm just picking a committee, I'm not designating a certain position like I did last time. It's combinations of 30 choose. Oh, I didn't state in this. I can't remember what we did in class. Okay, how many ways can you pick a committee of, let's say, 7 people? I don't know. So that would be 30 choose 7. You find this combinations button in the same place. It's in your permutations or your probability part of your calculator. The one thing I want to comment though, that combinations is used a lot in math and they have a separate notation for that. It can look like this. It can also look like this, 30 choose 7. And they put parentheses around it. It's not a fraction. Don't put a fraction bar there. It's just 30 choose 7 in parentheses. We automatically assume if it's that notation that it's combinations, not permutations. If you do it in your calculator, I goofed it up, sorry. I have 2,035,800 different ways I could come up with that committee. How many ways can you pick 5 cards from a deck of 52? This is why that combinations is handy. When you're picking cards, and that's a lot of time where you're doing probabilities and card games and that any kind of gambling situation, But I don't care what order I get my cards, because I'm going to immediately take those cards and rearrange them in my hand anyway. I'm going to change them up. So the order does not matter when you're dealing with cards. This would be 52 cards. I'm choosing 5 of them. And then you just type it in your calculator. Combinations. How many different Mega Million lottery tickets are possible? All right, Mega Million lottery tickets. That is the thing, and you're too young to buy lottery tickets, I know. Maybe your parents buy them, but there are 5. When they do it, I write the ball because it's like this. It's like when you play bingo. There's this big rolling tumbler thing that has all these different balls in it that have different numbers, like ping pong balls, and they have different numbers on them, and they pull them out of there. And those are all numbered 1 to 70. Then you have this other little rolling thing that has all these ping pong balls in it that are numbered 1 to 25. Those are the mega balls. And you are hoping to get, that's like a red one, and then you have to have the 5 of the other ones. The order that you pick these numbers does not matter. You know, you're picking your grandma's birthday and your dog's birthday and all these special dates. The order that you pick those numbers does not matter. That's why it's combinations. Now, if you look at the combinations, how many ways could you choose, first of all, of the 5? Well, there would be 70 options, and I have to choose 5. And then I have to pick the right ping pong ball out of the other rolling tumbler, and I'd have 25 of those, and I have to just pick one. Just got to get the right one out of that. And this is an and, so I'm going to be multiplying those different values together. Type 1 in my calculator, type the other one in my calculator, multiply those together. And it's going to be some crazy huge number. There, I just paused it when found. 302 million different Mega Million lottery tickets could be created from those numbers. Not very likely you're going to win. So let's talk about how likely is it that you're going to win. How many successful sets of numbers are there? So how many different winning lottery tickets are there? Well, to be honest, there is one. There is only one. Now, I wrote it as how many successful sets of numbers there are, because what happens sometimes is 2 people from different parts of the United States pick the exact same set of numbers. It happens. And so sometimes there's multiple winners because multiple people picked the same set of numbers, but there's only one successful set of numbers out of how many total different. Well, that's what we just did. Here's this turning this into probability, but having to use this combination to come up with the denominator. So we have a 1 in 302,575,350 chance of winning. Don't do it. It's not likely. But it's so